In these problems, we're dealing with a property of the graphs of functions called concavity, where the graph is concave up or concave down. And at this point, you know that a graph of a function, it's got slope, and slope is an interesting thing. Tells us how fast the function is increasing or decreasing, and it's the first derivative that gives us the slope of that tangent at any point, so we can see how fast the function is increasing or decreasing at any point along it if we can take that first derivative. Now concavity, you can sort of think of it as, well, I think of it as cuppiness. So you have this sort of cup shape and it's pointing down there. But if you get over here, the cup shape is pointing up. So this area of the graph is concave down. Somewhere, maybe right in here, it changes to concave up. And if it goes off further, maybe it'll change again. We have some more concave down, some more concave up. Well, it's the second derivative that tells us about concavity of the graph of a function. So if you want to tell where a function is concave up or concave down, all you have to do is take the second derivative. Where the second derivative is positive, the function is concave up. Where the second derivative is negative, the function is concave down. Let's see how this works with an actual problem. Here we have the function f of x equals x to the fifth minus 15x to the fourth plus 60x to the third minus 648. And we're going to go ahead and take the first derivative of that function. Let's see, we get 5x to the fourth minus 60x to the third plus 180x squared, and the 648 just disappears because that's a constant. And then we'll go ahead and take the second derivative. So this is f double prime of x, and we've got 20x to the third minus 180x squared plus 360x. Now, if we want to find where this is concave up and concave down, you need to find where it changes, the inflection points. So that point on a graph where it changes from concave up to concave down is called an inflection point, and those points are the zeros of the second derivative. So just as we would find the critical points by taking the zeros of the first derivative to see where the function changes slope, and you have your relative maxima and minima, here we're going to find the inflection points by finding the zeros of the second derivative. So let's see if we can go ahead and do that. We can factor this quite a bit. Let's see, I can take a 20x out of everything, and that leaves me with x squared minus 9x plus 18, I think. And so this term right here gives us a factor of x equals 0. And then we've got, let's see, yeah, we can factor this. So x minus 3, x minus 6. So we also have x equals 3 and x equals 6. So these are our inflection points, the places where we can look for concavity to be changing from up to down or down to up. And we can put these on a number line and then find the regions to test. And remember, we'll be testing by plugging into the second derivative, so this guy right here. So let's try, well, I'll make a little chart here so we can keep track. So this is x and this is f double prime of x. And all we really need to know is whether it's positive or negative, so we might not crunch out all the numbers if we can figure that out. Let's see, in this region I'll put in -1. That's going to give me -20 minus 180 minus 360. So that's clearly negative. So this is negative and this is concave down. So I'll make a note here, concave down there. All right, and let's pick a number for this interval. I think I'll choose 1. That should be easy. So we'll get 20 minus 180 plus 360. That's clearly going to be positive, so that's concave up. And let's see, in this region, I'm going to choose 4. Now the numbers are going to get kind of big on me. Let's see, so I think this is 1280. And this is 2880. And this is 1440. You might want to double check my math on that. And that looks like it's going to be a negative number, so this is concave down in this region. And then finally, we need a number out here, so I'm going to pick 7, and we get 68. 60 minus 8820 plus 25, 20, and that looks like it's going to be positive. So that's up there. Okay. So we've found all the regions where this is concave up or concave down. If we want to give the answer in interval notation, we would say it's concave down on the interval of -infinity up to 0, and from 3 to 6. And it's concave up on the interval, looks like a 5, let's try that, on the interval of 0 to 3 and 6 up to infinity. All right, let's try one more. This time I think we're going to start with a rational function, just to add a little extra challenge. So we want to take the second derivative of this thing. I've got a negative sign out there. I'm going to put that negative sign on the 25 so I don't lose track of it. And I think I'll use the quotient rule on this one. And the quotient rule says low d high. So I've got 9x squared plus 12. And the derivative of what's on top is just a constant. So that's actually 0. So that term is going to disappear. Very nice. Then I've got my minus high d low. So minus a negative 25 times the derivative of what's on the bottom, and that would be 18x. And that is all over low squared. So 9x squared plus 12 quantity squared. So this term disappears, and we've got a negative and a negative, so that's a positive. So I end up with, let's see, 25 times 18. I think that's 450x over 9x squared plus 12 quantity squared. So that's the first derivative. Now we want to take the second derivative. So we'll apply the quotient rule again. So low, that's 9x squared plus 12 quantity squared. D high is times 450 minus high, so that's 450x. D low, so we're going to use the chain rule here, and that's going to be 2 times the quantity 9x squared plus 12 just to the first power, because we reduced that power by 1, times the derivative of the inside, and that is 18x. Whew, that's a lot going on up there. And that's all over this quantity squared. So 9x squared plus 12 squared squared is to the 4th. Now let's see if we can do some simplification here. Remember, we want to find the zeros of the second derivative. So if we can make this a little simpler, it might be easier to find where the numerator is 0. One thing I notice is that I've got a factor of 9x squared plus 12 in each of these. So I'm going to take this one out, one of these out, and one of these out, so that becomes to the 3rd. And then let's see. Well, I can certainly pull out a 450 from everything. So 450 times 9x squared plus 12 minus, now I've got 2 times 18 times x, 36x squared. And that's all over 9x squared plus 12 quantity cubed. Now let's see. Well, if I simplify this a little bit on top, I've got, so that's negative 27x squared. I'm adding the 9x squared and negative 36x squared, plus 12. And that's all times 450. But I can also pull a 3 out of there, so I would have negative 9x squared plus 4 times 1350. And this really doesn't matter, and nor does the bottom, because really we're trying to figure out where the denominator, or where the numerator is 0. But this is a fairly simplified form of the second derivative. But I want to find out where the numerator is going to be 0. So where is this factor going to be 0? So I'm just going to pull out that negative 9x squared plus 4. to where I have a little more room here. So negative 9x squared plus 4. If that chunk of the numerator is 0, the whole numerator is going to be 0. And so let's set it equal to 0, and I get, so I could subtract 4 and then divide by a negative 9. So I would get x squared equals 4/9, or x equals positive or negative 2/3. Whew. So those are my inflection points. Now we just need to determine where it's concave up, where it's concave down. So here's negative 2/3 and positive 2/3. And 0's in between. And if we put in 0, well, let's see, the bottom is going to be, the bottom of this, here's kind of the simplest form we had of the second derivative. The bottom is going to be positive. If we put in a 0, we'll have 12 cubed there. And the top, so that negative 9x term goes away. It looks like it's going to be positive there. So I think this is concave up on that interval. And then we could take a negative 1 and figure out what we're going to get here. So that gets squared. Here we have a negative 1 squared, so the negative 9 plus 4 is a negative 5. It's going to be negative on top and positive on the bottom. So that's a net negative, so that's going to be concave down. And the same thing will happen because when we plug in a positive 1, it gets squared. It's going to act the same as the negative 1 did. So it's going to be concave down here as well. So I kind of ran out of room here, and this is looking really crunched. But we have our interval now from negative infinity up to negative 2/3, and from 2/3 up to infinity, it's concave down. So it's concave down from negative infinity up to negative 2/3, and 2/3 up to infinity. And it's concave up on the interval negative 2/3 to 2/3. So that was some work with using the second derivative to find the intervals of concavity. My name is Larry. I'm a teacher at EdVision's Off Campus. It's an online project-based school in Minnesota. If you're interested, you can check us out on the web at lovethischool.org. Thanks.